we are not as intelligently advanced as we think we are. The space telescope we built has captured amazing images of space. It turns out that it's so powerful that it may even have challenged our understanding of the universe. Before the Big Bang, the universe underwent a cosmic expansion at least 80 times in a fraction of a second, resulting in a tremendous inflation. This expansion turned out the cosmos barren and cold, halting its growth and transforming a vacuum energy into matter and radiation, marking the beginning of the Big Bang era. During this period of intense heat and density, the elemental building blocks that would eventually coalesce into the galaxies and stars we observe today were formed. The James Webb Space Telescope has explored the distant past of the universe, revealing an unexpected discovery that challenges our understanding of the cosmos. What was there before the Big Bang? This finding has stunned the scientific community and raises fundamental questions about the nature of the universe. Before the Big Bang, the universe did not exist and was created in an event that occurred approximately 13.82 billion years ago. Our galaxy, the Milky Way galaxy, is just one of about 2 trillion galaxies that formed from the remnants of the Big Bang, essentially islands of stars in the vast cosmos. Despite initial resistance from some scientists, the evidence for this sudden creation is hard to ignore, as evidenced by galaxies scattering like cosmic bullets and the afterglow of the Big Bang still detectable in the form of microwave radiation, known as a cosmic microwave background. In 1965, the analogy is put forward that the Big Bang did not take place at a specific point, but that the universe emerged and expanded simultaneously in all directions. This event did not occur in a pre-existing vacuum, as the fabric of space-time manifested with the expansion of the universe. A common comparison of the universe is to imagine it as an expanding pie, where the raisins represent galaxies moving away from each other without a central point of origin. However, unlike a pie with a finite boundary, the theoretically eternal universe has no discernible boundary. During the inflationary period, the vacuum contained an energy that increased proportionally to its volume, like a stack of bills that doubles or triples in value with each doubling or tripling. This inflationary energy is dissipated randomly, giving rise to the creation of matter and the heat characteristics of the Big Bang. This inflationary vacuum, which was essentially infinite, gave rise to our Big Bang universe as one of among an infinite number of bubble universes. This process began with a small amount of inflationary vacuum, and quantum theory suggests that phenomena such as these can rise seemingly out of nothing. However, the Big Bang theory still presents limitations and challenges. Although it is reasonable to assert that the universe began in an extremely hot and dense state, it has been expanding and cooling ever since. Uncertainties remain about how it fits various observations and exactly how it originated. Nevertheless, cosmologists have had to make adjustments to the Big Bang theory. According to this theory, the expansion of galaxies would be due solely to the gravitational attraction of matter. However, if this were the only process at play, the time required for galaxies to form would be considerably longer than the estimated 13.82 billion years. To address this discrepancy, astronomers have proposed the existence of invisible dark matter, which supposedly accumulates up to 6 times more mass than visible stars and galaxies, thus increasing the rate at which galaxies develop due to gravity. Although the fundamental Big Bang theory suggests that the expansion of the universe should gradually slow down due to the gravitational pull of galaxies. In 1998, astronomers discovered evidence that this expansion is accelerating. It is speculated that this acceleration could be caused by the presence of dark matter, an imperceptible form of energy that fills space and exerts a repulsive gravitational pull. Furthermore, the reason why the universe maintains a constant temperature requires additional adjustments to the fundamental Big Bang hypothesis. Astronomers suggest that the universe may have started out smaller than expected, then underwent an extremely rapid initial expansion in its first fraction of a second, known as inflation, caused by an inflationary vacuum, a highly energetic form of the vacuum that was already present in space. Considering the possibility that the Big Bang was not the first event to occur, the James Webb Space Telescope has captured a stunning image of that tiny corner of the universe, revealing previously unknown information. The purpose of the telescope is to detect light emitted by the first stars and galaxies, in the hope of gaining more details about the earliest moments of the universe. This breakthrough occurred on Christmas Day 2021. The main goal of the James Webb Space Telescope is to detect light emitted just after the Big Bang, when stars and galaxies began to form. This powerful telescope, which has been seeing development for 25 years, is considered the successor of Hubble, with a capacity 10 billion times more powerful. Since its launch, it has captured stunning images of galaxies that formed just a few 100 million years after the Big Bang, as well as the moment before the birth of a star. In addition, the James Webb Space Telescope has captured the first direct image of an extrasolar planet that has been used to photograph the Tarantula Nebula, a region rich in young stars not previously visible to the human eye. It has also revealed new hidden structures and fine details of huge gas clouds, such as the pillars of creation. Recently, an image of NGC 346, Heart of the Small Magellanic Cloud (SMC), a dwarf galaxy located 200,000 light-years from Earth, has been published. NGC 346, already known as a stellar nursery, offers a unique view of conditions during cosmic noon, a time when stars formed faster due to stellar dust. Although the star-forming zones were thought to be dust-free, the scans of NGC 346 show the opposite: the presence of massive dust clouds that accelerate star formation. According to Margaret Meixner, lead scientist of the study, NGC 346 is the only major cluster in its galaxy that is actively generating stars at present. This provides a unique opportunity to investigate cosmic noon conditions. The abundance of dust in NGC 346 supports the hypothesis that galaxies during the cosmic noon were also covered with dust, providing a close window into the early universe. In addition, it is suggested that NGC 346 may be generating planets as well as stars from swirls of metallic dust. This finding implies that Earth-like planets may have formed much earlier in the history of the universe than previously believed by astronomers. The new image captured by the James Webb Telescope is certainly a marvel, considering that the machine has barely been in orbit for a little over a year and has already managed to live up to all the expectations of all the designers and planners, regardless of the complexity of the chemistry and stellar physics involved. This stunning image adds to a growing collection of breathtaking panoramas beamed back to Earth by the James Webb Space Telescope. In addition, this instrument has enabled scientists to study the infancy of the cosmos, making a surprising discovery about the existence of 6 huge galaxies that existed between 500 and 700 million years after the Big Bang, radically changing our understanding of galaxy formation. The James Webb Space Telescope uses infrared light to probe the universe, since this wavelength is undetectable to the human eye and allows it to capture the faint light emitted by ancient stars and galaxies. With this amazing capability, the observatory can literally go back in time to 13.5 billion years ago, challenging our preconceptions about the early formation of the universe. Scientists need to rethink how galaxies formed and evolved, as the data collected show that these galaxies are much larger than expected from current models. This challenges the prevailing idea that galaxies began as small clouds of stars and dust that evolved over time. Although it is believed that the galaxies observed with the James Webb Space Telescope data may be somewhat later, it is crucial to keep an open mind about what we are observing, as this is our first look at such far distances. While the data suggest that they are likely to be galaxies, there is a possibility that some of these objects are hidden supermassive black holes. In any case, the discovery of a much larger than expected amount of mass indicates a significant change in our understanding of the universe, even if we reduce the sample size. There are several reasons why astronomers could have erred in their estimates, such as more efficient methods of star formation than previously believed. This could have fooled the James Webb Telescope into interpreting the stars in these galaxies as older as they really are. The James Webb Telescope has discovered new clues about what happened before the Big Bang, challenging some current scientific theories. The Big Bang is a theory that the universe began as a very hot, dense point, and that it expanded and cooled, allowing stars, galaxies, and other structures to form. The theory is based on evidence such as Hubble's law, which shows that distant galaxies are moving away from us, implying that the universe is expanding. The age of the universe is estimated to be about 13.8 billion years old, but the James Webb Telescope has made an exciting discovery about what happened before the Big Bang. What really happened before the Big Bang? We invite you to join us to explore this exciting discovery by the James Webb. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to the channel, be sure to like this video, and turn on the notification bell. The cosmic microwave background radiation, CMB, is a faint radiation that fills the entire sky and is a remnant of the intense heat and light of the early universe. The uniform temperature of the CMB is about 2.7 Kelvin, with small fluctuations indicating density variations in the plasma. The CMB also shows that the universe was opaque to light until about 380,000 years after the Big Bang, when atoms formed and light could travel freely. The abundance of primordial elements such as hydrogen, lithium, beryllium, and boron matches predictions of the Big Bang nucleosynthesis. The galactic distribution reflects how matter has clustered under gravity over time, forming stars and galaxies from small fluctuations. The oldest galaxies are found near the edge of our observable universe, and galaxies have different shapes, sizes, ages, and composition depending on their location in history. The younger objects are closer to us, while the older ones are at the limits of the observable universe. The problem with what happened before the Big Bang is one of the biggest challenges in cosmology. The Big Bang theory describes how the universe originated in a hot, dense state, expanded and cooled over time, but does not explain what caused or preceded this initial state. Scientists have proposed several explanations, such as the Big Bounce, the periodic X scenario, and the pre-Big Bang scenario. Each of these theories proposes different causes and events that led to reorigin of the universe. The pre-Big Bang scenario is based on the string theory, which is a framework that links all natural forces and particles. On the other hand, the boundaryless proposal suggests that our universe has no boundaries in space or time, and that the Big Bang is a soft zone when the size of the universe becomes very small. According to this theory, the beginning of the cosmos is described as a quantum fluctuation from nothing using quantum physics and a wave functions that encode all the potential histories that determine the structure and attributes of the universe. It is important to note that these possibilities are not mutually exclusive and may be compatible or complementary in some aspects. One of the major scientific goals is to find out how the universe formed, and the latest discovery of the JWST, the proto-galaxy cluster ever discovered, may help to achieve this goal. In theory, the universe has a hierarchy in how things unfold, and in the early phases of the hot Big Bang, all matter and energy were uniformly dispersed throughout space, with small perturbations superimposed on that uniform background. These oscillations are caused by the cosmic inflation that preceded and set up the Big Bang and exist on all cosmic scales, from the smallest to the largest. As matter and radiation interact and the universe expands, fluctuations on the smallest and intermediate scales have peaks and valleys in the density of time. Fluctuations in the universe can wax and wane, and the largest fluctuations on cosmic scales can be observed in the microwave background, which contains information about overdense regions that began to develop gravitationally. Gravity does not act uniformly throughout the universe, and its effect is restricted by the speed of light, which means that an overdense region in space will only attract nearby matter at a given time. The farther away matter is, the longer it will take to feel the gravitational pull. The size of the cosmic scales increases with gravitational attraction, from star clusters and galaxies to groups and clusters of galaxies. Once a large-scaled region experiences gravitational attraction, gravitational collapse must occur for a bound structure to form, and at the center, receding matter must cause such collapse. The density of the overdense zone must increase approximately 68 times for the large-scale structure to stop decaying and begin to collapse. Eventually, a bound object composed of subcomponents that form a large-scale structure will form. The first formations to collapse are molecular clouds of gaseous dust atoms and dark matter, which give rise to the first stars and star clusters. The densest regions can take 200 to 250 million years to collapse, while regions with higher initial overdensity conditions can collapse in as little as 50 to 100 million years. Star formation emits radiation and winds that create complex environments and make it difficult to predict details about these early structures. The first massive galaxies in the universe form from this merger of these structures. Richly evolved galaxies have been detected 320 million years after the Big Bang, and the JWST is expected to reveal populations of immaculate stars and earlier galaxies on a broader cosmic scale. However, disordered physics plays little or no role in the size of individual galaxies. However, allowance must be made for continued stellar production, enormous stellar winds and radiation, stellar deaths and cataclysms, cooling and falling gas and other atoms, matter fusions and ionization, and the interaction of dark matter with normal matter. When it comes to the formation of galactic groups and clusters, these factors have very little impact, and the formation is largely determined by three well-known factors: the expansion of the universe, the magnitude of the initial overdensity on the relevant cosmic scale, and the interaction of multiple cosmic scales. Whatever happens inside a galaxy, sometimes derisively referred to as gastrophysics, has no effect on the creation and growth of galaxy clusters. Only gravity matters. Before JWST, there were a variety of methods for discovering these galaxies. Throughout cosmic history, the simplest and most straightforward method was to identify a large number of galaxies that existed in the same field of view at identical redshift distances, but with significant velocity dispersion. The redshift method is used to discover and study distant galaxies in the universe. It is based on the principle that light emitted by moving objects is shifted towards longer wavelengths, for example, towards the red end of the electromagnetic spectrum. This phenomenon is known as redshift and is due to the Doppler effect. When a galaxy moves away from us, the light it emits is redshifted, which means that the characteristic spectral lines present in a spectrum are shifted towards longer wavelengths. This redshift can be measured by analyzing the spectrum of light arriving from the galaxy. Astronomers use spectrographs to scatter the light at different wavelengths and then examine these spectral lines. If they find a significant redshift in the spectral lines of a galaxy, they can determine that the galaxy is moving away from us and estimate the speed at which it is moving away from us. The redshift is expressed by the parameter z, which represents the ratio of the measured wavelength to the wavelength emitted by the galaxy. The higher the value of z, the greater the redshift and the greater the distance the galaxy is located. By measuring the redshift of many distant galaxies, astronomers can map the distribution of galaxies in the universe and study the expansion of the cosmos. They can also estimate how far galaxies are and obtain information about the evolution of the universe over time. The clustered galaxies were moving at velocities of several hundred or even a few thousand kilometers per second relative to each other. This method facilitated the discovery of nearby galaxy clusters, such as the Coma cluster of galaxies and the Virgo clusters of galaxies, which are heated, for example, by the collision of fast-moving gas clouds or by intense star formation processes that release X-rays. Modern science explains the origins of the universe within the Big Bang theory. According to this theory, the universe arose from the explosion of the singularity. The singularity is a point in the fabric of space and time where the concentration of energy and matter becomes extraordinarily high, reaching almost an infinite level, while the spatial and temporal dimensions are reduced to near-zero values. However, recently the James Webb Telescope has made a bold announcement that the universe has existed uninterruptedly and that the Big Bang theory is wrong in its approach. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, hit the like button, and turn on the notification bell. The concept of singularity describes a state where neither time, space, nor matter existed. The question that arises is where this singularity came from, what preceded it, and what even triggered the event that culminated into the Big Bang. It is debated whether the universe has existed eternally or whether it had a definite starting point. The singularity that preceded the Big Bang event contained the entire mass present in the universe, and this resulted in the complete suspension of the flow of time. This aligns with the perspective proposed by Albert Einstein, which suggests that debating what happened before the Big Bang is meaningless, since the notion of a before had no place. The idea that the universe is not expanding in empty space may be difficult to conceive. This conception is based on a theory known as the Einstein theory of general relativity, which he developed in 1915, and which remains to this date our best description of space and time. This theory is the foundation for many of these interesting and peculiar ideas. The theory of general relativity is supported by evidence such as the expansion of the universe, which was discovered by American astronomer Hubble in 1929. In addition, there is the cosmic microwave background radiation, which is uniformly distributed throughout the universe and was discovered by the American scientist Spenzias in Wilson 1965. The discoveries support the basis of our current understanding of the evolution and the nature of the cosmos. This radiation emerged approximately 379,000 years after the Big Bang, in a period known as the hydrogen recombination era. According to the Big Bang theory, in its earliest moments, our universe was tiny, no bigger than an atom. In times past, the notion of nothingness was a sustainable state. Asking how long it lasted is irrelevant, since during this period the concept of time simply had no existence. In this era, our world emerged from a random quantum fluctuation that emerged from the void, which represents a significant level of depth. Perhaps a question of greater relevance might be whether this quantum fluctuation was truly random, as Einstein famously put it in his famous phrase, "God does not play dice." With this notion in mind, it is interesting to reflect on the implications of this. What prevents another small fragment of energy-filled void from appearing again, leading to a new Big Bang? There is a possibility of this occurring with a 100% probability, which could annul the existence of mankind. In the multiverse theory, the emergence of life occurs through a natural phenomenon in which universes with parameters conducive to more black holes will have a greater chance of generating offspring, thus increasing the probability of life being present in those universes. Recently, renowned physicist Brian Cox explored the fundamental question of how the universe began. Cox presented the Big Bang theory, but in return, challenged the conventional perspective by introducing a fascinating approach, the idea of the existence of a time before the Big Bang. This intriguing notion expands our understanding of the origins of the universe. The notion of a pre-Big Bang universe connects to the theory of cosmic inflation. According to this theory, the universe underwent an exponential expansion in an extremely short period after the Big Bang. This significant growth allowed the universe to become uniform indeed, explaining its observed homogeneity on a large scale. Although inflation remains a fundamental part of the prevailing cosmological model, Koch's idea of a pre-Big Bang state adds a layer of complexity to the chronology of the evolution of the universe. One question that arises is what could have caused this primordial energy to trigger such a sequence of events? Could it be the result of interactions between forces that we do not yet fully understand? Koch's ideas about the time before the Big Bang are supported in the work of Roger Penrose, an outstanding mathematician and physicist who was awarded the Nobel Prize in Physics for his contributions to the understanding of black holes. Although his focus is on black holes, Penrose also introduces the concept of eons, which occurs in a cyclic framework. Each eon begins with a Big Bang, followed by a period of expansion, contraction, and finally a big crunch, in which the universe returns to its original state. This cyclic cycle sets the basis for a new eon, perpetuating itself indefinitely. Penrose's eon theory revolves around black holes, celestial objects of enormous gravitational force that emerge from the collapse of massive stars. Over time, these black holes evaporate through Hawking radiation, releasing energy. Penrose speculated that dead black holes from earlier eons may still exist today, leaving possible imprints in our observed universe. These remnants Penrose called Hawking points, in honor of Stephen Hawking and his contribution to the understanding of Hawking radiation. The late physicist Stephen Hawking's proposal could offer clues supporting the existence of states prior to the Big Bang. Roger Penrose's idea of Hawking points could represent a potential clue to the existence of a pre-Big Bang universe. These enigmatic points, which are about 8 times to the size of the Moon, refer to slightly warmer areas in the sky that can be detected by advanced observational techniques. While Hawking's concept of the dots stands out in the scientific conversation and highlights the fluidity of our understanding of the beginnings of the universe, the discussion also highlights the importance of scientific exploration and the potential for paradigm-shifting discoveries in the future, as with any revolutionary scientific proposal. Brian Koch and Roger Penrose's exploration of a time before the Big Bang faces challenges and controversy. Critics argue that the concept of a pre-Big Bang universe remains speculative, as it lacks direct observational evidence. In addition, the cyclic nature of Penrose's eon theory raises questions about the conservation of energy and the ultimate fate of the universe. Some skeptics question the feasibility of an infinite cycle of eons, as this could conflict with the laws of thermodynamics and other fundamental principles of physics. Now let's delve into another related theory, the multiverse hypothesis in cosmology. This notion suggests the existence of multiple universes, each with its own physical laws, constants, and properties. Well, the basis of this idea lies in the beliefs that our universe could be one among many in a vast and diverse multiverse. The concept of the multiverse has gained momentum as a way to explain certain aspects of our universe that seem to be finely tuned for the existence of life. Scientists have observed that the fundamental constants and physical laws governing our universe appear to be carefully balanced to allow the emergence of life as we know it. From this observation, some have proposed the anthropic principle, which holds that our universe has the characteristics it does because it must be capable of hosting intelligent observers like us. And well, let us know your opinion in the comments box. If you liked the video, remember to like and subscribe, and I'll see you in the next one. Thank you so much for watching.